So, welcome back. And today, as I promised, I'm going to talk about the Biot-Savart Law and its application. Calculate the magnetic field on the axis of a current carrying circular loop. So here I have the x, y and z axes, the three-dimensional system, in which I have a loop carrying a current I, and my loop is placed in the YZ plane. And when I look from here, the point P under consideration, then we see that the sense of the current in this loop is anti-clockwise. Okay. If I see from here, then the same will become clockwise. Okay. So I'm looking from this point P, which is at a distance x from the origin of this circular loop. Okay, and here I have a ideal element, a DL element, and DL element is always taken in the direction of the sense of the current, which is considered to be a continuous flow. It is a steady current that we consider there. Okay, and that is due to the flow of positive charges, which it is not. Okay. Now I have a certain DL element, and this is in this plane, so it is perpendicular to this thing. R and DL are contained in a certain plane. Okay, and then we use the Biot-Savart Law to see as to what will be the net magnetic field due to Biot-Savart Law, which is obtained over here. Now you can see that I have shown here is dB due to this small current element, DL element, which is carrying current, and this is, as you know, this is perpendicular to this vector R over here. So all points are from here at a distance R from here, and OP is equal to X. Okay. R is the radius of the loop. Okay. For the loop, the radius is capital R. So from geometry we can see that since this is X and this is R, so this small r is equal to under root of X square plus R square, or R square plus X square. Now, once we consider that this dB element is there, the dB, I can resolve it into two parts. One along the x-axis, dBx, and the other perpendicular to the x-axis, and that is dB perpendicular. Okay. So I can say that dB is perpendicular to the DL element, and dB is also perpendicular to R. Okay, because there is an element called DL cross R. Okay, and the product of a cross product is always perpendicular to the two vectors. A cross B is equal to C, where C is perpendicular to vector A as well as vector B. Okay. Here, look here. So B will be the vector sum of all the dB that we obtain due to all ideal elements, all of them, vector sum. So that means we have to carry out some kind of an integration or summation, right? There is another thing that I would like to add, and we understand that there is a free space, so that we talk in terms of mu naught. Okay, so you can see that the Biot-Savart Law gives the magnitude of its contribution dB as mu naught upon 4 pi I, and then the magnitude of dl cross r cap divided by r square. Okay, so I can write this as mu naught I dl, because theta is equal to pi by 2. So sine of theta will become equal to 1. So I can write mu naught I dl upon 4 pi r square plus x square. Now all these perpendicular elements, dB perpendicular, they will cancel out, because for every dl element there is a diagonally opposite dl element for which the dB perpendicular value will be cancelling out. Okay, so that is there, and that is because of the beautiful property of nature that's called symmetry. Right? Now dBx, all dBx elements will add up. They are in the same direction, so it will be a simple addition, simple summation, simple integration that will carry out. And dBx is equal to dB cos of theta. You can see that theta is the angle that has been shown over here. This angle is equal to the angle that makes with the y-axis. R makes with the y-axis. So theta, and then you can see that this is also theta, right? And then alternate angle that is there, theta, and this becomes equal to theta. Okay, you should call your geometry to prove that this and this, they are equal to each other. It's very simple. So I write dBx, the magnitude is equal to dB into cos of theta, and cos theta, you can see this is r and this is the hypotenuse. This is the base and this is the hypotenuse. So I can write it as equal to, okay, r upon small r, which is equal to under root of r square plus x square. Right, sir? Okay, so I can sum it up as dB value I can write here, from here, mu naught I r 4 pi r square plus x square raised to the power of 3 by 2, and this is multiplied by dl. So for every dl element, the value of dB will be equal to this, because r is the constant and x is also a constant here. Right now, if we take it further, then of course the value of dB will change, right? So the variable is dl. So when I want to add up the dB values, then exactly what will happen? We will integrate this dl over the entire circular path, and that will become equal to 2 pi capital R, which is the circumference over here. So I just multiply this quantity, whole quantity, by 2 pi R. I'll just do that because I'm running out of space. I'll do it here shortly. So then from this relation, when I integrate dl over the loop, I get d is equal to mu naught IR upon 4 pi r square plus x square raised to the power of 3 by 2. This is a kind of a constant right now. and integral dl over the loop. And when I carry out the integration over the loop, this is going to be equal to 2 pi r. It's known to us from our geometrical knowledge. So this is what we get, and 2 pi and 2 pi will cancel out. So I'll get B is equal to mu naught I r square upon 2 r square plus x square raised to the power of 3 by 2. So this is the relation that we'll get in general. Now, so it means, look here, this is more than r. Okay, so there is some kind of a relationship that exists, inverse relationship with the distance. Okay, so now we can just study this. If x is equal to 0, P shifts over here at the point O, at the center of the loop. And then at the center of the loop, if I substitute the value of x equal to 0, then here I get r cubed. So I get mu naught I, and r square will cancel with r square over here, so I am left with B is equal to mu naught I upon 2r. Okay, this is the relationship which we ought to remember. And there is, now I don't have the means to show you circular path, but I'll just take a part of this circular path, okay, and this tip is going to show the, or better is still if I take this, okay, this is the part of the circular path in which the current is passing. Now what we are going to do is, I am going to use my right palm, and you know that the current from here is anti-clockwise, so I hold it like this and I keep my thumb in the direction of flow of current. Then you can see that the lines of field, they will inside, the lines of field or the field lines will come like this out of this loop. Okay, so if there is a loop like that, and if we consider it as a magnet, okay, and the lines of field are coming like this out of this loop, coming like this, so there is a very simple question: which side will be the north pole of this supposed magnet and which side will be south pole? And lines of field, they go from the north pole to the right, to the south pole. So if you ask, in the first instance, an average student who is not very conscious about it will say that this is the north pole and this is the south pole, because lines of field, they come from the north pole and travel towards the south pole. Okay. But there is another thing, and there is another criteria, that in a magnet the lines of field enter a south pole and exit out of a north pole. So friends, our north pole in this case will be towards me, okay, and the south pole will be in the other direction. So this is about the single single loop. If there are n loops, then over each other, okay, then the field will multiply n times, okay, and we will have to introduce an n factor. If n is 10, then you will have 10 mu naught I upon 2r. Okay, so you can see that the magnetic field at the center of the ring is proportional to 1 upon r. Proportional to 1 upon r, and of course is directly proportional to I. The more the I, the more the field the more the value of R, okay, the less will be the field. So that kind of a thing you have to say it several times to yourself to understand these things. I just top it up, okay, with a very simple thing, a simple thing that I'm going to talk to you about, and that is very simple, okay, and it's not that simple too. Let me have two wires, straight wires, which are carrying current in this direction and in this direction. This is wire number 2 and this is wire number 1. Okay, let us take a certain point over here. Okay, so due to this wire, if I hold it, and this is the current direction, and I call this current I2, although I2 and I1 may be equal. I'm just introducing you to problems like that. So what will happen at this point P? At this point P, there will be two magnetic fields. One will be B due to the current I1, which I will call B1, and the other will be B2. Okay. Now I want to show the direction of B1 and the direction of B2, the caps. So see, I have this wire and I hold it like this because the current direction is like this, and my fingers, they point outside. So the magnetic field due to I2 will be outside, and that is, can be represented like this. Okay, and if I hold I1 like this, then my fingers are going inside, and therefore the direction B1 cap, this will be like this. Now when we map the points over here, then at some points the magnitude of B1 will be more than the magnitude of B2, depending upon the value of I1 and I2, but there will be certain points, for example, maybe a set of points which can be represented again by a line, okay, wherein the value of B will be equal to 0. These are neutral points, and if you remember, the neutral points we did calculate in the case of two charges, Q1 and Q2, and we obtain, if the two charges are of the same kind, the same variety, there is positive or both of them are negative, then inside there will be a point where the electric field will be equal to 0. So I am just introducing this thing, we will return to it later on. And particularly we can see that I will argue to you that these two wires carrying current parallel to each other, we will check whether they attract or they repel. And like, if this is positive and this is negative, the two charges Q1 and Q2, then also you see that the neutral point will be on the side of the smaller of the two charges, okay, whether smaller is here or smaller is here in magnitude. So if it is smaller is here, then it will be here, and if it's smaller is here, then it will be here. It cannot be found anywhere along the line joining the two charges. So these are certain things, and this is Biot-Savart Law is just like the Coulomb's law, which gives us the electric field, except that what we discussed in the last lecture, that the exception is there, whereas in the case of Coulomb's law, the line joining the 2 points, the 2 charges, the electric field will be along that line, okay, the test charge, etc. But here the electric field may be into the board or out of the board depending upon the situation. Okay. So that is the similarity. Now remember that in the discussions of electrostatics we had Gauss-Bae, G-A-U-S-S, Gauss-Bae. Gauss was honored with the unit of magnetic field later on. The most very intelligent person, Mr. Gauss. But there was an equally intelligent person, his name was Ampere. He is honored by the unit of electric current, a fundamental unit, and this Mr. Ampere, he came out with his circuital law, which is similar to the Gauss law. Okay? In Gauss law you have Q upon epsilon naught, and here we will find that there is I, mu naught I kind of a thing that will come up. Okay. So those things we do talk in the next lecture. For today, thank you very much. See you.